Okay, I guess we can start now. There'll be more people joining as we go to the next couple of minutes. Thank you, everyone, for... let me just start the recording as well. Thank you, everyone, for joining today's training session. I hope you all were able to catch our previous training session. If you did not catch it, we've also published it on our website, on our YouTube and our Vimeo, so please follow on there. Today we will be looking into an introduction to shells and how you can do or design and analyze parametric shells in Karamba3D. This will once again be recorded and also be published on our website at a later date. I have also shared the script for those of you who would like to follow on, and we will now start with a quick presentation. I will address questions at the end of the session if there are any, so please feel free to post any during the session and I will address them at the end. So today we're going to be looking into shells, as I mentioned. I touched on this last week, but we always have our Grasshopper scripts organized on our example page with the following sort of color grouping, with the input geometry in this dark gray, dark blue, the model entities, which are the basic Karamba elements, cross sections, materials, supports, and loads in green. Anything that relates to calculation, be it an analysis or optimization of the cross sections, in yellow, and results are in red, be it the model view, the shell view, or even all of the separate results components themselves. All of our Grasshopper files can be also found on our GitHub resources for download. So for shells, we follow a very simple standard setup as well, which is very similar to the beam example that we touched on last time. But for shells, we always start with a geometric input. This is when you're working in Rhino or Grasshopper, typically NURBS surfaces. However, when we do an analysis in Karamba, we have to convert these NURBS surfaces into meshes or triangulated meshes. Karamba has some native components that allow you to convert this, for example, the mesh breps, where it allows you to also control the density or the size of the mesh faces. Then once we've converted your mesh into a shell, we can define a cross-section. Either it's a standard constant cross-section or a variable cross-section per face. Next, we can define a material for that cross-section. And of course, we need to then define supports, which are point supports and support conditions, and of course, our loads. Everything is assembled in the assemble model, and then we can run an analysis or an optimization. And lastly, of course, we visualize the results using the model view. And this time we're going to go look into the shell view for visualizing shells. So I just noticed I put the wrong heading there, but in this example, we're going to be looking at a simple sort of 2.5D shell, where we're going to be manipulating the curvature of the shell and seeing how the results adapt to the input geometry. I'm going to be also showing you the legend component here too, and how we can adapt the cross sections and materials as well. So just a quick overview of the script. We start with a quick run through of how the geometry is created parametrically, then going through the separate parts of the different entities of our model, and then how we analyze and visualize the results, of course. So now we'll jump into the live script. So if you have opened now the Grasshopper script, you will see our script is organized as such. And we'll zoom in first into the geometric input. So with the geometric input, we first start off with generating some points, which we are going to use to create a NURBS curve. So the first two inputs are actually 2 points, which you can see here in my Rhino viewport. I'm generating a point at 0, 0, 0 and 10, 0, 0. Of course, this can be done parametrically should you wish. Then we want to create a center point of the 2 points. So I'm using the average to find the center of those 2 points. To be able to then create a curved, basically curve and not a line, I have a parameter that controls the Z coordinate of this point. So now if I was to click this, I can now see that my point is moving up according to the slider value. These 3 points are merged together into one list, making sure that my first point is a 0, 0, the midpoint is the second point, and the last one is my endpoint there. And then I'm using the interpolate to simply draw a curve between those 3 points. Of course, you can also use the NURBS curves component to also do such a to create a curve as well. And lastly, to create the plate, I'm doing a simple extrusion in the Y direction. My Y vector here has a slider attached to it, so I can control the depth of my plate here. So let's set my Z value back to 0. And so this is going to be my geometry that I'm analyzing in Karamba. As I mentioned before, we want to convert this into a mesh. So I'm using the mesh BREPS component, and this is found in the utilities tab here, the mesh BREPS. Those of you who might have the work in progress enabled, we are actually currently working on a much more in-depth mesh BREPS component that allows you to do mesh refinement as well. But currently I'm using our old mesh BREPS, which allows us to set the mesh resolution, which is basically the size of or the goal size of our mesh faces. And so if I now click on my mesh BREPS component, and I can see my mesh edges here, to make sure if you don't see them, you can also go to the display and also go to preview mesh edges to toggle this on and off as such. This mesh BREPS component is now giving me a mesh with 502 faces and 12 vertices. And this is now brought into my create surface element. So we're bringing it now into Karamba and converting it into an actual element. And I'm giving it a ID just for good practice, even though I only have one element here. Next, we want to define a custom cross-section. If you don't define a cross-section, Karamba will use the default cross-section, which is a 1 centimeter steel plate, basically. Here we can define the cross-section by setting the cross-section component and picking from the list the shell cross constant. Here you also have the opportunity to set a variable cross-section, or if you also want to define a reinforced concrete with reinforcement layers. We use a slider to set the height, basically the thickness of our shell, and we can also apply additional information should we want with the family name or color, for example. And I'm using the material selection to then select a steel material for my cross-section. For my supports, because we have our surface, I'm going to define supports at the ends, basically, just at the 4 corners of my surface. Of course, if we wanted to analyze it as a proper plate at all of the ends, it would be actually more beneficial to actually extract points along the actual edge. But in this case, what I'm doing is I'm going to extract the points on one side of the original edge and the other side, and define different support conditions for both sides of my plate. So here you can see I can define, I've set 5 degrees of freedom for my points on the left side, and on the right I've basically allowed rotation. I'm merging them for good practice to collect my data, and then this is now placed in the support component and plugged into the support input in the assemble model. Lastly, I'm going to define a couple of different loads and load cases. So the first one is gravity. So using the simple loads component to select gravity here, and I'm setting a load case gravity. Next, I want to now define a mesh load. So mesh load, I'm actually using the original input mesh as my load. And so this can be used to, for example, define if, let's say in the context of a building, a load of, for example, the build-ups or live load on this plate, for example. In this case, I've just called it roof, and we've set a basically a vector or a force of -1 kilonewton per square meter. Here we also have the opportunity to define if we want to set the orientation of our loads to global, local, or global projected. And we'll see later on what happens when we do that, when we have a, let's say, curved surface. And in the case of generation, we can generate them as points or line loads. In this case, because we're working with a mesh, only point loads will be generated on our mesh. Lastly, I'm also going to create a small wind load, which is actually defined as a strip on one end of our element. It's also parametrically linked, so it creates an actual extrusion from our surface. So if I was to then, for example, increase the height of my shell, you can see that it actually increases as well. And this load is now applied as a global load in the X direction, basically ignoring the actual mesh orientation, but taking in consideration the actual global orientation. And this is now what we call wind load case. These are then collected together in the load component, and we're plugging it in the assemble model here. As always, we get the total mass already calculated after we assemble the model. And let's go in and do our first calculation. So once we do the first calculation, here we can see it gives us a warning that there is one rigid body mode in our system. So most likely we have some issues with our supports. I can see that I have very, very high deformation as well. And you can see we have 3 different results shown in the maximum displacement. This is because we have 3 different load cases. If we wanted to analyze a certain load case, we can actually input, for example, this as a text into the load case, and you can see that we only have the result now for maximum displacement there, for gravity load case. Let's have a look at the actual model and the performance of it. So now we go to the model view. Let me unplug the gravity here, and we can turn on our displacement, and we can see how our model is displacing. So set to 1. Let's have a look at also which load case we're visualizing. So in this case, as you can see, we're looking at the gravity load case, but we can also select different load cases if you wanted to view the results in different load cases. So gravity, we can see that the arrow for our loads has been shown there. Let's maybe just make the arrow bigger so you can visualize it more. And let's turn on the load value so that we can actually see what our load multiplier is. So for gravity, you can see it's 1. And for wind. You can see how our load has been applied and distributed on the edge of our shell now. And we have the roof, which is basically a consistent mesh load on our entire plate. Because I'm using the same, let's say, mesh for the application of our load, you generally would see a more, let's say, uniform distribution of a load. Sometimes, depending on the density or the size of your mesh faces, you might see issues with how your load gets applied to our mesh. And I can show you how this happens is if I would, let's say, copy, if I make a copy of my mesh B-reps, and let's increase the density to, let's say, 1.1, and let's apply it now to our mesh there. And as you can see, when we apply a much coarser mesh with much higher sizes of our mesh faces, you can see the distribution is much more different and much more, let's say, coarsely applied to our mesh. And this also applies for when you're working with mesh loads on beams as well. So always be careful to when you're working with mesh loads on your elements. I'm going to set it back to the original one. As usual, we have the standard annotation tags where, for example, you can have look the cross-section name or the material name. And in this case, I think we didn't give a cross-section name, so that's why it's not even showing it there. But if we go to our cross-section name, we can give it a name. And we will then see it in our model view component. If we want to see the material, you can see the material also shown as such. And let's now look at the shell view where we can actually visualize the results mapped onto our plate. So in this case, we have the render settings. And here, for example, you can have a look at the cross-sections. This will just give you a mesh, a thickened mesh with the cross-section that you've applied. The thickness is basically, it's then mapping the thickness after, and this is typically useful for when you're doing an optimization of your cross-section so that you can actually see what the thickness of your cross-section is. The stress-strength ratio here. So as a standard, negative in compression, positive in tension. And so here you can see 2.7% in compression and tension currently. And then we have the mapping of the displacement. And sometimes you might see that my colors do not really match with my legend. And this is because we have actually the mesh of the model view also underlaid below. So what I would recommend is then if you want to really show displacement, because it's mapped onto your axis geometry, we should go to the annotations and remove the element axis there. And then you'll see it much nicer in the Rhino viewport. Of course, you can then have a look at the principal stresses in the first and second direction. And with the principal stresses, it's also important on the positions of your results. So 0 maps basically the results at the center axis of your shell, but we can also map the top, which is 1, and -1, which is the bottom. In this case, you don't see too many varying results too, but often in, I think, let's see which. You can actually see the results there. So in the -1, so at the bottom of our shell, and at the top of our shell for the principal stresses. And lastly, you can also display the layer axis if you want, if this is important for example, orientation of your joints, for example, or of actual elements on that you orient according to your shell later on. So let's go and now adapt our model slightly so that we can see how our model is then, for example, deforming. So if I now fix it in the Z direction, also there, you can see the deformation shape, of course, would adapt according to our support condition. And now we no longer, of course, because we fixed it now in the Z2 there, there's no more rigid body modes issue in our problem, or in our model analysis. We can, of course, set the height. And in this case, I'm looking at the principal stresses. So let's go back to the stress strength ratio, which we can actually see it mapped onto the cross section of our shell. And of course, we would expect that by increasing the cross section of our shell, we would then, of course, make it much stiffer and more efficient. Let's also, for example, change the material, concrete, and then you can also see how the stress strength ratio is then adapted to our concrete. Just the note, for example, this is concrete that does not have reinforcement inside of it, so it has very, very low tensile strength if you were to look into the material properties of this concrete material. I want to now go back to the original steel 1 centimeter. And let's go and change also our initial starting, let's say, geometry. And so here we're starting with the flat plate, right? And we're, for example, visualizing the gravity load case. But if we now, for example, start to add a tiny bit of curvature, you can see the results already significantly help. But of course, there is a sort of maximum, there's a sort of fine line between what is an optimal shape and where it starts to become more inefficient, as you can see as well, based off our stress strength ratio. And you can see this is adapting, and there's like a small fine line where approximately at 0.7 or this sort of parabolic shape or arc-like shape, right? The most efficient, of course, for gravity load case is then shown. Of course, depending on which load case you would visualize, and if we were to look at wind, we would have much different results as well. So this is where we can then also compare different load cases with the parametric input to really evaluate the performance of our geometry at different, let's say, heights of the shell, as you can see here. And of course, this is then controlling the thickness, sorry, not the thickness, the depth of our shell or the plate. And of course, as I mentioned at the start, we're not analyzing it as a sort of support at the entire length of our shell. So now if I was to go to gravity load case, you will see that it starts to deform sort of like a sort of fabric or piece of paper where it's held at the four corners as such. And by releasing rotation, it also has great effects on the deformation shape too, as you can see in this case. Lastly, I wanted to just go over the loads. So let's go and turn off the deformation, and let's set our height to, for example, 1.2. And let's have a look at the roof load case. Yeah. And let's have a look to see what happens when we change the orientation of our roof load case. So at the moment we have global, maybe let's turn on also the load values, although it can be a bit small to see, but we can already see that our loads are there. Maybe just to make it a bit easier to read, I'm just going to multiply my load by changing the slider to 10, for example. So our load has been multiplied by 10. And let's set now to local to mesh. And so here you can see our mesh is oriented as such where our positive Z direction is actually facing downwards. And so a negative vector on the mesh would be in this direction. And you can see all of our loads are now oriented according to the mesh normal at that specific vertex, as you can see. And lastly, there's also the global projected, which is what you would typically use when working with snow loads, for example, or wind loads, depending on how you apply your wind loads, where basically it's projected onto your input geometry. And so depending on the actual inclination of your mesh or your beams, the load is applied accordingly as it's projected onto your geometry. And so it's important how you define the orientation of our loads. So with that, this is all I wanted to share in today's session as a quick introduction to shells. I wonder if there's any questions from the audience. At the moment, we don't have any upcoming training sessions scheduled, but we will definitely be launching more in the next months. So definitely stay in touch with our website or on our newsletter so that you can see when our next training session will be happening. Otherwise, if there's no questions from the audience, I thank you everyone for joining me today, and we will be sharing this session afterwards on our website. And of course, if there are any suggestions for future training sessions or requests for videos or examples, please always get in touch with us, email us. We're always open to requests. Thank you very much for joining today. And yes, there was just a question now. Is it possible to connect many shells to work together? Yes, definitely. So here I've only shown one, but for example, if you have a B-rep that you connect with many different shells, then it would analyze it as, for example, a stiff element. If you were to apply joints, then there's actually a a line joint component that allows you to apply joints between your shell elements. I believe we do have a video that explains how the line joints works. So please take a look on our website. Otherwise, on our menu, we also have a detailed explanation and examples of how to apply this as well. And so this allows you to apply hinges with certain stiffnesses on your joints between shell elements. Are there any other questions? Okay, so if there's no other questions, I would like to thank everyone for joining once again, and hopefully see you in a future session. Have a great day.